Problem 10.7.2. Determine the directions of the principal axes having an origin at point O and the principal moments of inertia for the triangular area about the axes. So to find this, first I'm going to find the moments of inertia in the xy coordinates. Now for simplicity, I'm going to say, hey, this is a triangle. I've seen that before in this list, specifically this right here, to find the xx and xy components. So looking right here, xx is bh cubed over 12. By the way, it is a coincidence that that looks like the moment of inertia for a rectangle. It just happened to be that. So 1/12 the base of 9 inches and times a height of 6 inches cubed gives an xx moment of inertia of 162 inches to the 4th power. Now for this formula for the y, that looks kind of complicated. But if you'll notice in this picture, we're dealing with a right triangle, which means that this distance right here, which Wikipedia is calling a, is equal to b. So this is b cubed h plus b cubed h plus b cubed h. In other words, 3b cubed h over 12, or b cubed h over 4. So 1/4 times base of 9 inches cubed times height of 6 inches gives 1093.5 inches to the 4th power. Now, unfortunately, Wikipedia does not have this off-diagonal term for moment of area, so I'm going to have to calculate it myself. So the formula for moment of area is xy times dA, which I'm going to call xy dy dx. And I'm going to do this to say that I'm integrating y first. This line right here is y equals 2/3 of x, because it starts at 0, 0, ends at x equals 9 inches, y equals 6 inches. For every point on this line, y is 2/3 of x. So when integrating dy, or when integrating on y, remember we are integrating just finding the product of inertia for just this little strip right here. Our bounds go from 0 to that to that function. So 0 to 2/3 x. Whereas for the outer integral, we're looking at all possible values of x, so that goes from 0 to 9. So do the inner integral first. Remember, x is constant for this integral, so we pull it out. The integral of y dy is 1/2 y squared. Plug in our bounds, 2/3 x in for y. That becomes, this squared is 4/9 x squared, which when combined with this 1/2 becomes 2/9 x squared. And then when combined with this x becomes 2/9 x cubed. Now for the outer integral, the integral of 2/9 x cubed from 0 to 9 is, integrate this becomes 2/36 x to the 4th power from 0 to 9, plug in our bounds of integration, and we get that the IXY, the off-diagonal component, is 364.5 inches to the 4th power. All right, now that we have that information, the first thing, determine the direction of the principal axes. Now, I am going to most directly use equation 1010, but we could also do this by using a Mohr circle. Because in the Mohr circle, and if you want to follow along with this, look at page 555, figure 1019, the y component of that angle that is 2 theta p, the y component is IXY. And since I'm going to be going from across the diameter, I'll say that the y component is 2 times IXY. And the x component of that angle is the difference between IXX and IYY, or IYY minus IXX doesn't actually matter. So I can find this value. I can take the arctangent of that value, and I get 2 theta p, divide by 2, and I get that theta p, that is the angle away from the principal axes is 19.02 degrees. Now the other part of the question, what are the principal moments of inertia? We could again use the Mohr circle, or we could use the Imin and Imax formula from 1011. It ends up doing the same, meaning the same thing. So I'm going to do this from a Mohr circle perspective. First, to find the center of the Mohr circle, I take the average of the two diagonal terms. So 1093.5 and 162. And the average of those two is 627.8 inches to the fourth power. So on figure 1019, 627.8 inches to the fourth power, that is the location of O, of the origin of the circle. I can also find the radius of the Mohr circle. So going from O to, say, point A, I first go in the y direction. This is IXY. And then in the x direction, I go 1/2 the difference between the XX and YY components. And then use Pythagorean theorem to find the radius of the Mohr circle. And the radius of the Mohr circle is 591.4 inches to the fourth power. So if I rotate my axes by this 19.02 degrees, then the 2 points that represent these two should be points where IUV is 0. And so it's just IUU and IVV are the principal moments of inertia now. And those are equivalent to the origin plus the radius and the origin minus, or the center plus the radius and the center minus the radius. So center plus radius, 627.8 plus 591.4 gives 1219.2 inches to the fourth power. And center minus radius gives 36.4 inches to the fourth power.